Hello and welcome to today's lesson on Rutherford Scattering, which is part of the atomic structure topic in GCSE Separate Science Physics. So in today's lesson we're going to look at describing how we worked out the nuclear or planetary model of the atom by a Rutherford Scattering experiment. So if we're successful and we learn in today's lesson, we should be able to state the planetary model of the atom, state how we know this model from experimentation, and describe how our model of the atom has changed over time, which forms part of the GCSE specification in 4.4.1.3, the development of the model of the atom, which is in fact common content with GCSE chemistry. So to explain the atom and what it's made from, we must come up with a scientific model. Now the concept of a scientific model is extremely important in science. A scientific model is an idea or a theory which is used to explain observations and data made in experiments. Now there have been many models of the atom, from the first model, which is Dalton's atomic model of the atom, then Thomson's Plum pudding model of the atom, followed by Rutherford's planetary model of the atom, and then finally Bohr's energy level model of the atom. Now it's important in science that we keep continually updating our scientific models to fit with the latest experimental data. So in the future we may make amendments to the model of the atom based on our new experiments we carry out in the future. So the scientific method is the pathway we use in physics to update our models and ensure their accuracy according to the experimental results that we achieve. So the scientific method is as follows. Step 1, you would theorize a testable model or idea. Then you would, step 2, gain experimental values about this model or idea. And then after step 2 you would then alter the model or idea to explain the experimental values, and you repeat and you repeat and you repeat. Now it's important to note that this is the pathway we use to update our model of the atom. So Rutherford followed up his idea with the testable experiment and then modified his idea to explain his experimental values to come up with the model of the atom. And like mentioned before, the model of the atom is still being updated in the present day. We are still carrying out experiments to test our theories. So in science our model must be able to explain the observations that we make, and if the model does not follow the observations we must replace it with the model that does. This means over years of discoveries we have changed our scientific model, which is what happened with the atom. Now the first model which described the atom came from a chemist called John Dalton. So John Dalton theorized that atoms are indestructible and indivisible. They can't be divided into smaller parts. Now Dalton's model is very good for explaining the ideas of compounds, elements and mixtures. However, in 1897 the electron was discovered and was found to be inside atoms. This meant we needed to amend the model of the atom from Dalton's atomic theory. Because like we said before, scientific models have to change if the experimental results show that this model is wrong. So a new scientific model is created which can explain the experimental results. So we started off with Dalton's model, the idea of just a simple sphere for an atom. With this led to J.J. Thomson replacing the Dalton model with the Plum pudding model. So in this particular model, J.J. Thomson thought that there must be electrons inside the atom because he discovered the electron at Cambridge University in his experiments. So Thomson believed that the atom was made of positively charged matter with negatively charged electrons scattered throughout like plums in a plum pudding, which gives its name the Plum pudding model. So the Plum pudding model was the first attempt at redefining what an atom looked like, and scientists were desperate to see if the plum pudding model was correct. So it's a bit like a chocolate chip cookie. So in the theory of the plum pudding model or the chocolate chip muffin, Thomson reasoned that the plums or the chocolate chips were the negative electrons and the solid filling was the positive charge. Now in this idea, the plum pudding, the muffin and the atom are all completely solid. There's no space inside the atoms. So the chocolate chip or the plum represents the electron, whilst the muffin or the pudding represents the positive charge. Now it's important to note that in our plum pudding model we don't refer to the positive charge as protons. They had not not been discovered yet. And it's also important to note that the atom in this model is completely solid. There's no empty space. So in the Plum pudding model, there is no space in the atom. And this model was used to explain the experimental observation of the electron. And this model also explained why the atom is electrically neutral. It's not charged because the positive charge and the negative electrons will cancel each other out. So our Plum pudding model is an atom consisting of electrons embedded in positive charge. So with our new observations and data, we change to model 2 because a new model is always proposed if we need to explain new observations and data. So J.J. Thomson's Plum pudding model was a very important concept in the history of particle physics. It was our first guess at how the atom was constructed. Now Thomson's Plum pudding model is what we believe the atom to be until the director of particle physics at the University of Manchester, Ernest Rutherford, came along. So Ernest Rutherford wanted to test Thomson's Plum pudding model of the atom using his newly discovered alpha particles. So he carried out what we call the gold foil experiment or the Rutherford Scattering experiment in 1910. So what he did is he bombarded thin gold foil with a beam of alpha particles, and he expected it to be just like firing bullets in a tissue paper because the alpha particles are travelling extremely quickly. So he said if the positive charge was evenly spread out like Thomson says, the beam of alpha particles should easily pass through. So Rutherford got a layer of gold foil 1 atom thick. Now in reality it wasn't actually 1 atom thick, it was about a couple of hundred atoms thick because it's difficult to get a 1 atom thick layer. Now, what happened was, that the alpha particle is fired from a radiation gun such as uranium. Now, alpha radiation was a new discovery of science at this point, and it's a type of radiation emitted from a nucleus which increases the stability of the nucleus. Now, alpha radiation is also ionizing, which can mean it can ionize your DNA, which can mutate your DNA and can lead to cancer. So, alpha particles are ionizing or cancer-causing radiation. Now, an alpha particle is just 2 protons and 2 neutrons. Now we commonly call this a helium nucleus. So an alpha particle has a positive charge of 2. So it's a positively charged particle. Now Rutherford placed the gold foil and the alpha source in a vacuum chamber, and he fired the alpha particles at the gold foil. Now the reason why he placed them in a vacuum chamber is that the alpha particles would be ionized if there was air in between the alpha particles and the gold atoms, because alpha particles tend to stop within 5 centimeters of air. So if there was no vacuum chamber, the alpha particles wouldn't even reach the gold atoms. So what happened is Rutherford placed an alpha particle detector on the other side of the gold atoms, and he moved the angle in which the alpha particles were fired at the gold foil and measured what happened to the alpha particles after they passed through the gold foil. So the alpha particle detector was moved to different positions, and as a result he then observed where the different alpha particles were coming out. Now, like mentioned before, Rutherford expected the fast-moving alpha particles to smash straight through these plum pudding model atoms. And they expected this to happen because the alpha particles are fired out of the radiation gun at a very fast speed. The gold atoms are considered stationary, so he thought it would be like an artillery shell being fired through a piece of tissue paper. They should smash straight through. Now, what did happen when Rutherford fired his alpha particles at the gold atom? Well, he actually found that most of the alpha particles did pass through the gold foil like expected, but that is because the atom is predominantly empty space. So the first conclusion Rutherford drew was that the alpha particles went straight through the gold foil because the gold atoms in the foil are mostly empty space. A few of the alpha particles, as they passed through, deflected away from the atom as they did this. So as we know, there's a nucleus in the center, so the nucleus will also slightly recoil in this repulsion, but because this recoil will be much smaller because the nucleus is a lot more massive than the alpha particle, which is what we call due to the conservation of momentum. Now, the reason why our alpha particles deflected away from the atoms is because there must be a positive charge in the atom. Because the alpha particle itself is positive, so the only thing that can repel another positive charge is a positive charge. So the positive charge of the atom and the positive charge of the alpha particle repel each other. So the second conclusion Rutherford made was that the alpha particles, some of them are deflected away from the gold atoms because there's a nucleus in the atom which is positively charged. Now, about also 1 in 10,000 alpha particles reflected backwards off the atom. Now, they don't literally reflect, they repel off the gold atoms without actually touching them. So it can sometimes be referred to as backscatter. Now, this occurs due to a large repulsion between the positively charged alpha particles and the nucleus. Now, this large repulsion will only occur if the alpha particle is going to directly contact the nucleus, hit it dead on. Now, the important thing to note is only 1 in 10,000 alpha particles reflects backwards, so this indicates that the nucleus can't be that large. Now, if we compare the nuclear radius to the atomic radius, this showed us that the nucleus must be much smaller than the atomic radius. Now, if 1 in 10,000 alpha particles are reflecting backwards, that tells us that the nucleus of the atom is 10,000 times smaller than the radius of the atom, which is conclusion 3. So we know that most alpha particles go through undeflected, a few alpha particles are slightly deflected, and a few alpha particles bounce off, but not technically bouncing, reflecting backwards off the nucleus. So we can see this in the following animation. As a result, you can see the results from the Rutherford scattering experiment, or you can see it in this particular animation. Most of them went straight through, a few of them deflected to the side due to repulsion, and 1 in 10,000 would actually backscatter, would reflect backwards. Now, this was important because we compared the results expected if the Plum pudding model was true. Now, if the experimental results do not fit the old model, then Rutherford had to come up with a new model to explain the results. So Rutherford devised a new scientific model which explains the observations of the experiment. So observation 1, most of the alpha particles pass straight through the gold atoms. The reason for this is the atom is mostly empty space. Some of the alpha particles are reflected when they pass near the center of a gold atom. This indicates the nucleus is positively charged because the alpha particle itself is positively charged. And finally, about 1 in 10,000 alpha particles were deflected by more than 90 degrees. They move backwards because the diameter of the nucleus is 10,000 times smaller than the diameter of the atom. So to explain these results and observations, a new model was proposed, and this is what Rutherford suggested. Inside every atom is a nucleus. The nucleus contains all of the mass of the atom. It contains all of the positive charge of the atom, and it's extremely dense. Now, the nucleus contains most of the mass, yet has a radius 10,000 times smaller than that of the atom. So the results from this alpha particle scattering experiment led to the conclusion that the mass of an atom was concentrated at its center, the nucleus, and this nucleus was charged. So this nuclear model replaced the Plum pudding model. But this wasn't the end, because Niels Bohr adapted the nuclear model by suggesting that electrons orbit the nucleus at specific distances. Now, it's important to note that Bohr did this theoretically, but his theoretical calculations agreed with experimental observations. So this was an amendment to the nuclear model. Now, you'll also notice that Rutherford didn't actually ever use the word proton. He only actually discovered the nucleus in Rutherford's scattering experiment, but he carried out later experiments which led to the idea that the positive charge of any nucleus could be subdivided into a whole number of smaller particles, which each particle would have the same amount of positive charge. So Rutherford had discovered the proton. Now, finally, the experimental work of James Chadwick 20 years later in 1932 provided the existence to show that as well as there being positive protons in the nucleus, there was also neutral particles which had a mass. So James Chadwick had discovered that within the nucleus there were neutrons, which led to the familiar model of the atom which we know today, the nuclear model. So this tells us the atom has a positively charged nucleus, has a nucleus with a very small radius compared to the atomic radius. The atom is mostly empty space, but this nuclear model was amended when Chadwick discovered the neutron, which is found in the nucleus, and that the electron structure was amended when Bohr deduced the electron energy level structure. Now, when looking at the Rutherford Scattering experiment, we should be aware of the following. The conditions of the experiment. You need a vacuum and an alpha source and gold foil 1 atom thick. You need to know the results of the experiment. That most alpha particles pass straight through the gold foil. A few alpha particles deflected away from the gold foil, and 1 in 10,000 alpha particles undergo backscatter against the gold foil. And finally, you can come up with some conclusions. Most of the atom is empty space. The nucleus is a condensed mass in the atom with a much smaller radius than the atom, and the nucleus is positively charged. But why did the scientific community accept the work of Rutherford? So whilst it seems obvious now, the idea of an atom with a nucleus at the centre and lots of empty space was very weird to the scientists of 1910. So why did people accept Rutherford's ideas? So the first reason why Rutherford's work was accepted was because he was the director of physics at the University of Manchester, so he must have had some very good qualifications in physics. Next, he did the experiment thousands of times. So he did the experiment thousands of times and got these experimental results. So his results were very reliable. And finally, other experimenters around the world get the same results when they repeat the experiment for themselves. So the experiment was not only reliable, it was also reproducible. So Rutherford's work was accepted and his model was used in science as Rutherford was a respected scientist with a large body of work. The experimental results were repeated thousands of times by the experimenter, and finally the experimental results were reproduced by other experimental results. So what have we learnt in today's lesson? New experimental evidence may lead to a scientific model being changed or replaced. Before the discovery of the electron, atoms were thought to be tiny spheres that could not be divided. The discovery of the electron led to the Plum pudding model of the atom. The Plum pudding model of the atom suggested the atom was a ball of positive charge with negative electrons embedded in it. The results from the alpha particle scattering experiment led to the conclusion that the mass of an atom was concentrated at the centre, a nucleus, and that this nucleus was charged. This nuclear model replaced the Plum pudding model. Now, Niels Bohr adapted the nuclear model by suggesting electrons orbit the nucleus at specific distances, and his theoretical calculations agree with experimental observations. Later experiments led to the idea that the positive charge of any nucleus could be subdivided into a whole number of smaller particles. Each particle would have the same amount of positive charge, which we now call the proton. And the experimental work of James Chadwick provided evidence to show the existence of neutrons within the nucleus, which occurred 20 years after the nucleus had become an accepted scientific idea. Now, you should also be able to describe why the new evidence from the scattering experiment led to a change in the atomic model and the difference between the Plum pudding model of the atom and the nuclear model of the atom. So if we've been successful and learned in today's lesson, we can state the nuclear model of the atom. We can state how we know the nuclear model of the atom from experimentation, and finally we can describe how our model of the atom has changed over time. I hope you've enjoyed today's lesson on Rutherford Scattering, which is part of the atomic structure topic in GCSE Separate Science Physics. Thank you very much for listening to today's lesson and have a lovely day.